Now, this I think is really cool. This is what's called a biosynthesis of steroids. What this term implies is, how does a biological system synthesize compounds? So it's a biosynthesis, something in biology. All right, so here is the structure of cholesterol. It's a very complicated structure. A lot of our hormones have this type of structure to it, and steroids and things like that have this type of a structure to it. All right, and it comes from a compound called squalene. All right, this is a compound. You can actually already kind of see what's going to happen here. Squalene is a compound that our bodies make. Our bodies synthesize it. And it's basically a double bond followed by 2 carbons, and a double bond, 2 carbons, double bond, 2 carbons, double bond, 2 carbons, double bond, with other groups hanging off of it. But that's basically what squalene is. Okay. And then we have enzymes, epoxidase. Anytime you see something that ends in ACE, ACE, it's some sort of a enzyme. Okay. But if you pretty much epoxidize this double bond right here. Now, only an enzyme would be able to do that. It'd be very hard to selectively epoxidize that particular one. But anyways, if you epoxidize this, what basically happens is a cascade effect. What happens is the double bond attaches here, forming a carbocation right here. And then that double bond attaches there, forming a carbocation here, and so forth and so on. And it just goes dink, 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 and it bonds. It makes this structure just from epoxidizing that part. Okay? It's a really cool way of how our bodies make these cholesterol compounds. Here's kind of the mechanism of it. But you see the epoxide, protonate it. This is going to attack the more substituted spot because it's in acid. So that epoxidizes, leaving a plus charge on this carbon, which this is. Double bond, so you're forming a bond between here and here. All right, giving you now a plus charge there. This now attaches there, giving you a plus charge here. All right, and then that attaches there to give your 6,6,6,5 ring system, which is very characteristic of steroid compounds. So I thought this is a really cool way to show you why it's important to understand epoxide opening and how epoxides are used in our bodies and in a biological system. All right. The very last chapter is now adding Grignards or organolithiums to epoxides. Same type of analysis as we saw in the base catalyzed. These are bases. These are strong bases. So it's very similar to the base mechanism of the epoxide opening. All right. If you remember, these have negative charges. Okay. So based on that, they go to the least substituted position. Your alcohol goes in the more substituted because these are going to attack based on SN2 type of mechanisms. So least substituted spot. They're going to attack these carbons, that carbon right there. Okay, and pop open your epoxide. Okay, so notice your R group goes on the least substituted position, and your alcohol goes on the most substituted spot. Okay, and this is done in ether because we just learned, beginning this chapter, epoxides, I'm sorry, not epoxides, Grignards are very stable in ether. So ether is not really a reagent, it's just the first reaction is the addition of the Grignard in ether. The second reaction is the protonation of the O-. Okay, so that's basically it for chapter 14. A lot of it is review. Write down any questions you have. Any questions, write them down. Bring them to class the next time we meet, because that's all we're going to do. Answer questions. Questions, questions, questions. You want me to talk about something again? Questions. If there's a mechanism you understand. There are a few other things I do want to explain and go over a little bit more. But basically, you know, this is about 80 to 90% of everything that we'll be talking about in this chapter. We'll also do a bunch of synthesis problems and problems from the book. And again, watch this as many times as you want so that you really understand all the information.